Alright, welcome back. This time is going to be another longer video about a single type of problem. This is the playground area problem. Let's read the problem and see what we got going on. The local elementary school wants to build a new rectangular playground area outside for their students. One wall of the playground area is going to use the wall of the school, and the other three sides of the playground space will be made with fence. The school has 300 meters of fencing to complete the project. The wall perpendicular to the school wall should be labeled X. Number 1, write an expression for A of X, the area of the playground. Number 2, what is the area of the playground if X equals 50? Number 3, what is a reasonable domain for A of X? And number 4, what is the maximum area the playground can have? So let's start by drawing a picture. We know from the wording it says a new rectangular playground area. So we know that the shape's going to be a rectangle, and one of the walls is going to be the school wall. And the other three are going to be made with fence. So I'm going to draw a rectangle where three sides are like the same color because they're made of fence, and then the fourth side is going to be labeled the school wall. Gotta spell wall right. And then inside of that is the play area. Play area. And it goes on to tell me that the side perpendicular to the school wall is labeled X. So if this is X, then this one should be X. They should both be labeled X because they're the same, because they're a rectangle. And now, question 1 is sort of underway. We're writing an equation for A, the area of this, which is going to be length times width. I already know the width is X, so now I just got to come up with an equation for the length. And I'm assuming that I should try and make this playground as big as possible for kids, the play area, excuse me. So if I want to use all of my fencing and I use 1x for the left side and 1x for the right side, I've used a total of 2 x's. So now I just got to calculate the leftovers for this bottom side, which would be the total amount of fencing, 300, minus the 2x of fencing I've used. Total amount of fencing, 300, minus an x for the left wall, minus x for the right wall, is minus 2 x's in total. And that tells me the length. So my area formula is going to be the width, x, times the length, 300, minus 2 x's. So that's number 1. All set and done. Pretty standard, pretty easy. Number 2 now is, what if x is equal to 50? What's the area of the playground? And so I want to find A of 50, which means everywhere there was an x in my expression, I should replace with a 50. So that gives me 50 times 300 minus 2 times 50, like that. And actually, I'm going to drag this over so that I'm not writing immediately above my picture. And so I'm just going to simplify this and solve. So that's that outside 50 times 300. The first thing I can reduce is that 2 times 50, which is 100. And then I need to do that 300 minus 100 leaves me with 200. And now I need to do that multiplication of 50 times 200 gives me a whopping 10,000 meters squared of area. So that is the answer for number 2. What would the area be if x is equal to 50. So let's circle these. This is the answer to number 1. This is the answer to number 2. What happens if x is equal to 50? Now doubling back, question 3 asks, what is a reasonable domain for x? So number 3, we want the domain. Set of x values that can go into our function, the set of x values that can be used. So I'm looking for the biggest x value and the smallest x value I can use. So x is a distance. It's the distance away from the school wall that I'm going with my fencing up here. So if I was to make x really small, my play area would look like a really narrow hallway. For instance, if I made x to be 10, this would be 10 and this would be 10, and then I would have 280 meters left over of fencing for that long wall. But I could potentially go smaller than 10. I could do 1 meter of fencing. I could do half a meter of fencing. So I just basically need to be bigger than 0 because I have to go some distance, because x is a distance. I can't measure out a negative meter of fencing. I don't know what that means. So x should be bigger than 0. And now we're trying to think of what's the largest x can be. Well, and what would that even look like? So here's the school wall again, and if x was really, really big, for instance, if we made it, I don't know, say 120, each side was 120, that would use up 240, which would leave 60 left over to go across. So we could potentially make it really narrow the other way, away from the school building. But now this brings up an interesting point, that each time I'm using the same amount for the sides. So the largest it could be would be the way to make this the smallest, but to use an even amount on each side. So I'm using two x's each time. And so to find out how much I can use, I take the total amount of fencing I have, in this case it's 300, and I'm going to divide it amongst the number of x's I'm using, which is 2 x's each time. One for the left wall, one for the right wall. And that tells me I'm using 150 meters of fencing as the most I could use. So that would be a really long, away from the school wall play area, but it would have no width at all for the kids to play in. So there's the domain. 0, because that's the lowest distance I can measure, up to 150, because that's half of the material I have, and each half of the material gets used for the left and right side. So that's why I did it as a half. Potentially, if you were using 3 x's somehow and making some sort of weird triangle, you might want to do divide by 3, but in this case it's 2 again, 1 for each side. So there's the reasonable domain for this particular problem. If you had a similar problem but a different amount of fencing, that top value, the top value x can be, would just be the total amount of fencing you have divided by 2, 1 for the left and right side. I'm going to delete that, and now we need to make our way to question 4, which I believe asks for the maximum area the playground can have. Well, in order for us to find the max value the playground can have, I suggest we use Desmos. So we want max area. Max area. So what we're going to do is we're going to go to Desmos and we're going to graph this particular function and see what the area is. So, oh, I still got stuff set up from the last video. You guys don't need to see that. So the area was x times 300 minus 2x, like that. And now we want to think y values. We need to zoom out a lot. So x should be a number between 0 and 150, we said. And my y values should go from an area of 0. We saw 10,000 in one of our answers. So I'm going to say 15,000. There it is. So this purple curve, actually, should I zoom out even more? You guys are probably like, what is this guy doing? Let's go negative 50 to 300, and then we'll go negative 1,000. There we go. So this curve depicts the area of my play area. And this point, that 0, 0, represents if x was 0, we didn't go away from the school area at all. Our volume, or our area, excuse me, of the play area would be 0 because it has no width. And then the other, I'm sorry, it has no width. It has all length. And then this other point, the 150, 0, is if we made x as big as possible, it would be all width and no length. And now the point we're looking for in this case, we want the maximum volume, is right up here. That highest point tells us the maximum volume we can have, and it tells us the x value we need to make that happen. It's 11,250 is our maximum area. So 11,250 meters squared is our maximum area. There you have it. The playground area problem kind of summed up. If you got questions, leave them in the comments. If you've got another problem you want me to tackle, let me know. I'll see you guys next time. Bye.